Hi, and thank you for being here. My name is Camille Quinteros, and I'm pleased to present gestural design, hand tracking for digital drawing, developed along Jordan Cantor at the University of Massachusetts Amherst. Computational design is increasingly interested in the active feedback between the user designer and the digital space. And this is to be expected, since often as designers, our first impulse is one of a gesture that is physical, that it's embodied, and that it contains ideas of movement, texture, light. For example, the work of Constantine Brancusi or any other physical media artist are the product of a relationship between the mind and the body. It's part of a dynamic conversation and the mediation between the ephemeral that lives in our brains and the physical that lives amongst us. This process of making is tactile, is haptic, and it's embodied. Gestural drawing is part of the tools of architectural thinking, as it is exemplified in this really beautiful drawing by Zaha Hadid. It is called A Vision of Madrid. Her paintings too contain ideas of movement, of space, and they have been mediated by the manual ability to place oil on canvas. However, today's tools for architectural design entrap the designer in a mind-hand-click relationship, denying their body and the important mediation between concept and movement. So this project asks, can we translate gesture into the digital space, thus transforming the human-computer relationship as we consider it to be critical for creative output? What we propose is a feedback loop that goes from physical gesture to digital model and then back to physical through 3D printing. This provides the user with an opportunity to have a physical interaction with the gestural model and tweak accordingly. The proposal is one that incorporates bodies as gesture makers, as well as bodies as tactile feedback generators. Virtual reality is a plausible platform for this research. However, issues of economic accessibility and GPU performance requirements become immediately apparent. We sought to find an option that was nimble, that was open source, and that was universally accessible. Machine learning has been recognized as a viable alternative for gestural translation and human-computer interaction since as early as 1997. However, the development of machine learning had not achieved the desired results until recently, when in 2020, Google released the Hans MediaPipe library. Hans MediaPipe uses two methods of prediction. First, palm recognition. The question is there a palm in the image, or is there not? And if there is a palm in the image, is that the same palm that I was looking at before, or is it a new palm? And second, it uses a landmark recognition once it has specified the palm. This landmark recognition pinpoints 21 points on each hand. This approach is so nimble that Hans MediaPipe can be run with any RGB camera using as little processing power as the ones available on a cell phone or a mobile device. For our project, all we had to use was a laptop camera, and that was it. In the research, we tested a workflow for translating from physical hand gesture to digital point cloud model using MediaPipe hands and the computer webcam. Through a process of coordinate sampling and scaling, we were able to produce spatially accurate recordings of hand gestures. We then developed one possible process for translation of that point cloud into a robust geometry, and finally to translate that resulting digital geometry into a physical form via 3D printing. By closing the circle from physical gesture to digital form to physical form again, this research sought to initiate a feedback loop that could allow for an interactive exploration of the design possibilities in the intersections of physical gesture and digital geometry. The landmark recognition can be captured in each picture frame or at specific time intervals. By using picture frames, the resolution varies depending on the complexity of the gesture, while when using specific time intervals, the speed of a gesture is captured. Coordinate data was collected at regular time intervals. This has two advantages. First, since the frame rate of the hand tracking changes depending on the complexity or the predictability of the gesture at any given time, the timestamp sampling ensured a regular set of samples. Second, by sampling at a regular time interval, the velocity of any hand landmark can be calculated. This is the result of the distance between any two sequential points divided by the time interval, which would give us the velocity. This was taken advantage of in a subsequent process, which I will discuss. So with this decision settled, we generated an output matrix of XYZ locations for fingertips. So we focused on the fingertips. This came from the MediaPipe's hand Python script. It got captured into a CSV file, and with the XYZ locations, we can now start thinking about points in space and how those can be built in Grasshopper for Rhino. Now, the Grasshopper setup is incredibly simple. The Grasshopper script will read a CSV file, it will eliminate any undesired characters, and that data then is used to build points in space. But there is an intermediate process that needs to take place, which is scaling and validation. MediaPipe Hands is a 2.5D reader with a depth prediction, and it measures both width, height, and depth in pixels. So what we did is that we ran a series of test gestures, moving a hand from one side to the next, up and down, or back to front in known distances. And we use these reference gestures to create scaling factors to convert this 2.5D pixel-based coordinate into real-world coordinates. Once the scaled points in space are accurately translating a physical gesture, we can start to construct the points. And with points constructed, we can build a surface. Now, at this point, the project can go in a myriad of ways. Once the points in space are generated, it really is up to the computational designer to decide how to use and manipulate them. For our purposes, we were looking for a literal translation of hand movements into digital model. So we decided to connect each fingertip with a line and to loft those lines into a singular object. So let's see some examples. Here you can see gesture 1, 2, and 3. Each of them being the movement of a single hand in about 4 seconds. Each gesture becomes a surface through the process of CSV reading, scaling, point construction, line, and lofting. With these surfaces, they become kind of floating objects in digital space. We weren't quite satisfied here. We wanted to emphasize and highlight that these surfaces came from movement. So we enacted agents to crawl and flock on each individual surface based on velocity. The result is complex and data-rich models that capture an original expression and that can be further manipulated. The agent's behavior, which I said is based on velocity, it really is based on the proximities from each point to the next. If the landmark is too far away, the first from the second, then a second generation of agents is enacted who flock around the trace of the first generation of agents. What this strategy does is that we can highlight the areas where hands move faster, and we can de-emphasize the areas where movement is long and steady and much more subtle. To finalize the loop, we 3D printed 3 different sections of a model study. This first section is a knotted cavity, something that gets generated if fingers undulate around a central point like so. The hand doesn't move around the space, but the fingers move around a central pivoting spot. The second is an undulated sheet, and this is a condition that is generated from a consistent hand motion, all fingertips kind of together as they move through the space. And then the third condition, which is the curved head at the end of a digital model. So as you finish the model, closing the hand into a fist generates this kind of endpoint. The purpose of the project really is to open up the possibilities for embodied methods of design and to have a new human-computer relation. We want to shed away some of the frustrations that are carried by the complex setup as well as expensive nature of specialized equipment. Our attitude is one of using technology to free the user from hyper-specialized workflows and really to lean into the universality of gesture. We set out to design a workflow that translates hands into digital geometry and then back to physical form through 3D printing. In particular, the use of artificial intelligence and machine learning provides a platform to record and create robust digital models using just a laptop and a webcam. This presents a new avenue for reintroducing the intricacies, the individuality, the intimacy, and the expressiveness of hand gestures into the digital modeling process. This workflow suggests a much more inclusive approach to design and digital form making. It opens the possibilities for leveraging the universal language of hand gestures as a direct driver of design and processes of form making. This has the potential to liberate the designer or the design expert from the limitations of conventional user interface tools, such as a keyboard and a mouse, or having the exact knowledge of what you want your parametric model to do. This creates a much more embodied, less mediated user face experience. It also suggests the potential for non-experts to engage in the design process in a more direct way, allowing their own expressive gestures to be translated into digital and physical form. By tying this workflow into a broader network of DIY makers, artists, and designers, we are only expanding the possibilities of form making in the future. And with that, I just want to thank you for listening and for your time, and I really look forward to our panel discussion. Thank you so much.